It's March 20th. This is lecture 23. We're discussing Stewart section 8.4, which is other convergence tests, which is kind of a vague title. Remember that before break we talked about sequences, and then we talked about series and some basic examples of knowing how to determine if a particular series converged or diverged. And then on Monday and Wednesday of this week, so that was section 8.1, sequences, section 8.2, series. And then Monday and Wednesday of this week, we discussed section 8.3, which was some more tests for convergence. The integral test, the comparison test, and the limit comparison test. So those three tests. So today is just some more tests. So I'm going to start by just talking through this stuff. As I mentioned to some of you who were here earlier, all of this stuff on the board is in the book. The previous section, I wrote stuff out on the board so students would copy it into the notes, but it just takes forever, even though I think it's a useful thing to copy stuff out. I think you learn stuff by having to write these symbols. So part one of the meeting today, we're going to talk about alternating series. So remember that an alternating series is a series where the alternate terms have opposite signs. So the first thing that I want to discuss is the alternating series theorem. So it says this: if you have an alternating series, so that's going to be a series of this form, -1 to the n minus 1 times bn, where bn is a number, where the terms bn are all positive. So the alternating comes from just this -1 to the n minus 1 parked in front. So if you have one of those things, and if it satisfies these two additional criteria, that bn is a decreasing sequence and the limit of the bn is 0, then the series converges. Now that sounds reasonable enough, but remember that we've encountered series where the series of the terms going to 0 does not guarantee the series converges. So it's a big thing for alternating series to be able to have that simple criterion. Could you all put phones away, please? I'd like to not see phones out during class. And then some more terminology that's going to be useful. We're going to denote the sum of a series by just the letter s. So s is going to be add up all the terms. Remember we talked about last week the kth partial sum, s subscript k. So that means you just add up ending with the kth term. And I pointed out that in class they refer to the nth partial sum. And so what they do is for the whole sum they have an index of n, and n goes all the way to infinity. And then they talk about the nth partial sum where the index they use is k, and k goes from 1 to n. I find that confusing. So I like to use an index of n all the time. Either n goes from 1 to infinity, that's the whole series, or n just goes from 1 to k, that's the kth partial sum. And then a new thing is we're going to be talking about the error that you would incur if you made an approximation. So you're on a quiz, and you're being asked to add up a whole series. Well, it would take you a long time to add up an infinite number of things. So, you decide, well, I'm just going to do 100 of them or 50 of them. That's going to have to be good enough because I don't have time to do an infinite number of them. Of course, you couldn't do an infinite number of them. You can only do a finite number of sums. So what happens if instead of thinking about the whole series, you think about just the kth partial sum? How bad would that be? Well, that idea is the idea of the error incurred, or the remainder. So we introduced this term r subscript k. So the remainder of things that have not been added up if you just add up the first k terms. So the whole series minus what you get when you just add up the first k terms, and then take the absolute value of that, because we don't care if it's positive or negative. That's what we're going to call rk. And so to be clear, this means all of the remaining terms, so like the tail of the series that did not get added up. So starting with k plus 1 and going to infinity, all those terms are not included in this kth partial sum. So this remainder is the absolute value of that the absolute value of that tail. So we have a theorem about how bad that error is. If you approximate the series by just doing SK, well, that remainder is guaranteed to be this. It's pretty cool. I've asked everybody to put phones away, so if you put your phone in your backpack. So that's pretty cool, because remember, the remainder is all these terms that didn't get added up, the whole tail. There's an infinite collection of things in that series, starting with k plus 1 and going to infinity. So the amazing thing is, for alternating series, the remainder is less than just the next term. So if you add up, 933 terms, and you think, well, I'm tired, I'm getting carpal tunnel syndrome. How bad is this? How good is this? Well, just look at the very next term, the 934th term. That gives you a bound on how bad your error is. So that's pretty amazing. Okay, then some definitions. A series is called absolutely convergent if the series of absolute values is convergent. And then there's a theorem that says if you have a series that is absolutely convergent, so you have a series AN, where if you do this to it, you take the series of the absolute values, and that's convergent. If that's convergent, then this theorem says that the original series is also convergent. But the converse is not true. It's possible for a series to be convergent, but not absolutely convergent. We've actually seen series like that. So if you have a series that has that property, that it's convergent but not absolutely convergent, that's going to be called conditionally convergent. Okay, so and then here I've got some stuff we'll discuss in meeting part 2. What I want to do now is discuss an example where we use the concepts on that sideboard. So, this series from 1 to infinity of minus 1 to the n plus 1 times 1 over n. That's an alternating series. And that's convergent by the alternating series theorem. Now, why? Well, maybe before writing down that conclusion, so don't write down that conclusion. This series satisfies, well, Bn is equal to 1 over n, so those are positive. What else? Bn is a decreasing sequence. And also, the limit of those terms is 0. So this sequence satisfies all of those requirements over there in the hypothesis of the alternating series theorem. So we can write the conclusion that this series converges by the alternating series theorem. All right, so can somebody tell me, is this series absolutely convergent? Marcy?
I don't think so.
Can you say why?
Because since there's a negative value in the equation, the product, the terms can sometimes end up negative. So if it was an absolute value, then it wouldn't be the same as the non-absolute value.
Definitely wouldn't be the same but does it not? But do you have a reason to believe it would converge or not converge? That was a question. So do you have a good reason?
Well, that point wouldn't be an alternating series, would it?
Right. We've had series that are not alternating, but they do converge. So somebody else, if you have, yeah.
It's not alternating, we have harmonic series.
Right. Exactly. So the absolute value terms that is this series. And that's a p series with p equals 1. It's the harmonic series, so it diverges. So it diverges. The original series, so this series diverges. So the original series converges, but the series of absolute values does not converge. So the series is convergent, but not absolutely convergent. So this is the original series. Is not absolutely convergent. So the original series is conditionally convergent. So question, and notice, we proved this series was convergent because we used the alternating series theorem. We had to check these requirements, and then we used the theorem to say the thing converges. Now B, what about this series? From 1 to infinity of minus 1 to the n minus 1 times 1 over n squared. What can you tell me about that series?
Is it absolutely convergent?
Good. Can you explain why?
That would just become the p series with p equals 2.
Right. So notice we can just skip. We can just go for the big prize. We could go right to saying this is absolutely convergent. Because the series of absolute value terms, minus 1 to the n minus 1 over n squared, absolute value is this series. That's a p series with p equals 2. So this converges. So the original series is what we call absolutely convergent. Is it convergent in the regular sense? Well, come over here, look. Remember, this series We proved this is convergent by using the alternating series theorem. Had to check, check, and then we could say it's convergent. But that series over there, we figured out that it's actually absolutely convergent. So we have this cool theorem that says if a series is absolutely convergent, then it's also regular convergent. So we don't have to do the regular convergence test. So notice the absolute convergence test was pretty simple. And so therefore, the original series so let's call this star is also just regular convergent. So notice, it only took me one panel to get all that stuff, whereas that one I had to figure out that it was convergent using the harder test, the more involved test, and then I also figured out that it was absolutely convergent. Okay, question C. So suppose you want to approximate S, so that's this whole series, by the sequence of, by the series of partial, by the kth partial sum. So that would be just going up to k. And we want, so you're going to approximate this by only adding up a finite number of terms. You're going to make an error. I mean, there's going to be some error in not adding up all those terms. We want the error. Suppose we want the error to be less than 0.0001. How big a value of k can you give me a value for k that you guarantee will accomplish that? So the lowest value of k that you can guarantee will be good enough. So notice, we don't know the value of S. If we knew the value of S, we wouldn't be here. And we don't actually, I don't really want to compute Sk either. So remark, we don't know the value of S, the whole series, and we're not being asked for Sk. We're just being asked for k. So we're not being asked for the value of Sk. We're just being asked for the lowest possible k that we can guarantee. All right, well, let's think about what we're saying. Remember that what we call RK, that is this remainder, is the quantity that's the error that you make when you use an approximation of, instead of using S, you use SK. So that's that. That's the remainder. Or the error. Now, let's go back over to this board. Why is that called the remainder? Remember that when you approximate this series by just using a partial sum, that means you didn't add up a bunch of terms. You didn't add up the whole tail. So the remainder is the sum of those remaining terms. So that's where they get that's why the letter R, at least I think that's why the letter R is used. Okay, so we want RK to be less than 0.0001. Okay, but there's a theorem over there that says RK is less than BK plus 1. If you only add up the first K terms and you want to think about how much error did I make, all you have to do is look at the very next term. That gives you an estimate. So the strategy is to choose K so that BK plus 1 is less than 0.0001. So what would that get us? Well, then we'd have that the remainder, the error, by the theorem would be less than BK plus 1. That's by the theorem. And then we would make sure that that's less than 0.0001. This is by our choice of K. I didn't have my second cup of coffee. So we choose the value of K to ensure that this is true. The theorem guarantees that that's true, so that's how we're going to get our remainder to be low enough. Okay, so let's do it. We have BK plus 1 has to be less than 0.0001. So 1 over n squared has to be less than, now remember that's 1 over 10,000. 0.0001 is 1 over 10,000. Oh, so that means that, oh, and this should be this should be k plus 1 squared. K plus 1 over k plus 1 squared has to be less than 1 over 10,000. Well, let's flip everything over. That means that k plus 1 quantity squared has to be greater than 10,000. Let's take the square root of both sides. On the count of 3, what's the square root of 10,000? 1, 2, 3. Ooh, good. Marcy gets the new car. So k plus 1 has to be greater than 100. So what's the best value of k that we can think of? Well, let's go farther. K has to be some integer that's greater than 99. So what's our best bet for, what's the best k that we can guarantee will work? Yeah. So I can guarantee you, not knowing the value of S, not knowing the value of S100, I don't know what that would be. That would mean adding up 100 terms. I'm not going to do it. That's like for you to do on a quiz. So But I can guarantee you that if you use k equals 100, that's going to be good enough. You're going to commit an error that's within our desired bounds. Well, let's have a look. Let's have Wolfram do this. Dun, dun, dun. I told Wolf, and you guys use Wolfram Alpha? So in addition to help me cheat on my calculus.com, there's Wolfram help me cheat on my calculus.com. You can just type stuff in, and the cool thing about Wolfram is that it will tell you what it thinks you asked for. I mean, you can also do this on a handheld calculator, but good luck figuring out what to type in. Handheld calculators, I hate those things because you type the wrong thing in, you don't know. I mean, you have no idea whether you typed the right thing in. Whereas apparently I typed in the right stuff, computing the series minus the partial sum. The difference is, look at that, it's less than 0.0001. So if you use k equals 100. Now, remember, we don't know the value of s. We don't know the value of S100. I could get Wolfram to tell me that. But maybe there's a lower value of k that would work. Let's use k equals maybe 95. You want to get a little cheap. Oh, well, if I use only 95 terms, I'm still within, the error is less than 0.0001. What about, let's get crazy here. Let's go all the way down to 80 maybe. Well, dang it, even 80 terms would have been good enough. So what's so great about this stupid theorem? If I said, well, you got to use k greater than 100 or greater than or equal to 100, but it turns out you could have used k equals 80 or maybe even less. Well, the deal is here we know the true value and we know what S80 is and we compute the difference. The only reason that we know that 80 is actually good enough is because we know the true value. But if we knew the true value, we wouldn't need to do an approximation. So without having access to the true value, and you just have to come up with an estimate, the best estimate that we know how to provide is, I can guarantee you 100's definitely good enough. There might be some lower numbers that are good enough, but this one will work. So you could sit there with that program and you could just type in lower and lower values of k until you get to the lowest possible one. But that was not what this question's about. This question is about, without knowing the value of k, what can you say? All right, now that's meeting part 1. Meeting part 2, I want to talk about the ratio test. If you have a sequence that satisfies this limit equation, the limit of the absolute value of the ratio of successive terms is some number that's less than 1, then the series that you build from that sequence is absolutely convergent. On the other hand, if that limit is a number that's greater than 1, or that limit is infinity, or if the limit doesn't exist, then the series that you would build from that sequence is divergent. And on the other hand, if the limit equals 1 exactly, then the ratio test is not conclusive. It does not reveal anything about whether the series converges or diverges. All right, so I want to just do an example. So meeting part 2, example. I'm going to call this example 2. Consider the series from 0 to infinity of -1 to the n over 10 to the n factorial. Show that it's convergent by various methods. Okay. So method 1 is a ratio test. So the limit as n goes to infinity of an plus 1 over an, absolute value, that's the limit as n goes to infinity. I can leave off the minus 1s because they get killed in the absolute value. So I get 1 over 10 to the n plus 1 factorial divided by 1 over 10 to the n factorial. Well, dividing by a fraction, we just flip over and multiply. So this is the limit as n goes to infinity of 10 to the n factorial over 10 to the n plus 1 factorial. Now, what's 10 to the n divided by 10 to the n plus 1? I'm not going to call on Marcy. Marcy's not going to answer all the questions. Somebody else tell me. How do I simplify 10 to the n over 10? Come on, we got stuff to do.
It's 1 over 10.
Good, 1 over 10. Thank you. Now, somebody else. What's n factorial divided by n plus 1 factorial? Well, remember, n factorial is n minus 1, n minus 2, all the way down to 2 and 1. What's n plus 1 factorial? Well, that's n plus 1 times n minus 1, all the way down to 2 and 1. Oh, but look at this. This much is n factorial. So n plus 1 factorial is just n plus 1 times n factorial. So this ratio is just 1 over n plus 1. Now, what's the limit of that as n goes to infinity? It's 0. So the limit converges, so the series converges absolutely by the ratio test. All right. That's method 1. Method 2 is use the alternating series test. So the Bn is 1 over 10 to the n factorial. So this is positive. We definitely get that the limit, it's decreasing. Why? Because, well, let's see. B to the n plus 1 over B to the n is going to be Well, let's go through all that stuff. It's going to be 1 over 10 times n plus 1. That's less than 1. We already found out that the limit of this thing is 0, but if I just look at the ratio, it's always a number that's less than 1. So it's decreasing, it's positive, and the limit as n goes to infinity of Bn, that's the limit as n goes to infinity of 1 over 10 to the n, n factorial. That thing is 0. So it satisfies all three of the requirements for the alternating series test, so it converges. And then finally, method 3 is a combination of old and new methods. I love this example because it's just really good to experiment, to exercise all of your. Any of you volunteer at the dog shelter? Every day they got to get all those dogs out and exercise all the dogs. So we're exercising all the dogs. We're exercising all of our tests. So notice that the series of absolute values of Bn's, that's this series. That converges by the limit, by the comparison test. So we get 1 over 10 to the n, n factorial. That's less than 1 over 10 to the n, which is 1/10 to the n. So this series, which is this series 1/10 to the n, that's a geometric series. That converges. With r equals 1/10, which is less than 1. So this converges, which means that our original series converges absolutely. So this series converges. I'm running out of time here. But so this series of absolute values converges, and so the original series converges by the theorem that if something is absolutely convergent, it's convergent. All right, let's do our quiz. The quiz seems to be simple from what I could tell. So if you all would scoot out.